Right. So what we had seen was the Helmholtz and the Gibbs free energies. These were defined as such, right? And then I can see dA is equal to du minus TdS minus S dt, but normally we take these processes at constant temperature, so we can just get rid of the minus S dt, and dG is equal to dH minus TdS at constant temperature. Let me just write that somewhere. While defining dA or A, it was du minus TdS, which at constant volume was less than equal to 0. That was one of the criteria for spontaneity, and from there what we get was dA constant temperature, constant volume less than equal to 0, and dG likewise constant temperature, constant pressure less than equal to 0. Now at least one of you was wondering that at some point of time I say, for example, du is equal to S dt TdS minus PdV, and at other times I say du is less than equal to TdS, right? At least one of you did raise this question at the end of the class. So is there any controversy over here? How many of you feel there is a... It's just quite common to feel that way, but other than this girl and gentleman who raised this question, rest everybody doesn't find any controversy over here. Well, that's good then. But the thing is that this is the equation. Equation, whether it's reversible, irreversible, does not matter. This is the equation. This is the inequality. And how do I get, if I put dV equals 0, I'll get this. I get the equality, not the inequality. So how do you manage this? The idea is that when I am talking of TdS or PdV, I am always talking of reversible heat exchange or reversible work done. Remember, it does not matter whether I do it reversibly or irreversibly, the total change is the same. Yes? So, like I can write this is equal to dq reversible plus dw reversible, and it's equal to dq irreversible plus dw irreversible, right? Since du is a state function, u is a state function. But from this equation, I cannot write that dq reversible is equal to dq irreversible. dq reversible is given by TdS, and this is given by PdV minus PdV, right? But these are not. These depend on the path. So when I am saying over here, right, that this is equal to TdS minus PdV, and I put dV equals 0, and I managed to get TdS. Right. I take care to switch it off, so please do that. So right, so this is just the reversible heat exchanged. Right. If the work done is irreversible, then the heat exchange would be irreversibly, which would be du, right? And of course it should be less than the heat exchange reversible. across those 2 points. Yes? You'll find the same thing and the same logic applies to all of these equalities and inequalities. Right?
Sir, you said that when delta is 0, ds is 0, you have du less than 0.
Equal.
Less than equal to 0. Sir, I don't like that. I mean, entropy is constant at constant volume.
Remember, this is the entropy of the system. Okay? If the energy goes down, that means heat is released to the surroundings, which means the entropy of the surroundings must go up.
Sir, so the entropy of the system will go down.
It might go down, it might be 0. Doesn't matter.
Sir, but heat will go from system to surrounding.
Yeah, but the heat will go, right? But other than that, we also have a volume process. One example you have already seen.
Sir, but volume we have considered it constant.
Yeah, in that case it's constant.
So, it's only heat that is the question.
Mm-hmm.
So, ds can be 0 for the system. Heat is going out of the system.
Mm-hmm.
So, the entropy of the system will decrease.
Entropy of the system decreases. Entropy of the system stays constant in this particular case, right? What we had for du was volume and entropy is held constant. Volume of the system and entropy of the system are held constant. In that case, the criterion for spontaneity is that the internal energy of the system should decrease.
Sir, it is ejecting heat or both work can't be done since dV is 0. So, how is the internal energy different?
Right. So, what is the internal energy made of?
Let's say we have studied dV work and heat.
Right. And what else is there? Emotions. If I take an ideal gas, it's just the temperature. So the temperature of the system then has to change. How fast these molecules are moving. Okay. So this should be clear because sometimes it leads to confusion with some people. So one should remember that this is an equality, but from here I cannot say that dq reversible is equal to dq irreversible. Right? So that's where we get this from. That's where we get all of these inequalities from. Right? And all of these inequalities, what we have studied, are for TV work only. Till now. Okay, but there's no restriction. I can include the other kinds of work. Instead of just having PdV as dW reversible, I will have minus PdV plus work additional, which is always present. But for the case of for just keeping things simple, we restricted ourselves to media. Now, let's have a look at what exactly is this Helmholtz free energy and what exactly is the Gibbs free energy. Okay, so in case of, let's say, the Helmholtz free energy, what we write is, let's use the second law, TdS greater than or equal to dq, and the first law we had du is equal to dq plus dw, right? And then if I substitute the second law over here, then what I get is du is less than equal to TdS plus dW.
right? Or if I just switch it over on the other side, dW is greater than du minus TdS. Yes?
So, whatever the work is done by the system is always greater than du minus TdS, right? So, if I say work done by the system, then this is a negative quantity. It's a more negative quantity than this one. So, the maximum work that can be done by the system would be du minus TdS, because whatever dW is either greater than or equal to that. So, it's a less negative quantity. This is a more negative quantity if I say work done by. And mind you, over here I have not introduced the concept of PV work only. I just said dW. So, this is the total amount of work that can be done by the system, and this is nothing but dA at constant temperature, right?
So what I can write is that dW is greater than dA, which is identical to dW max. And for this reason, this A is also referred to as the work function. Right? Then I go on and tell you what is the significance of the change in the Gibbs free energy, dG. And dG is nothing but equal to dH minus TdS, right? dH minus TdS, and in general it would be minus SdT if I don't hold the temperature constant, and dH is given by d of u plus PV, right? du plus PdV plus VdP, and du is given by dq plus dW. So let me just write that, dq plus dW plus P minus plus PdV plus VdP minus TdS minus SdT. हाँ क्या हुआ? Okay, then I should write dH is equal to d of u plus PV, which is equal to du plus PdV plus VdP. ठीक है? And then I write du is equal to dq plus dW plus PdV plus VdP. ठीक है? Okay. So what we get over there is PdV plus VdP plus, it does not matter whether I do the thing reversibly or irreversibly. So just let's put it reversible. Reversible work done, reversible heat exchanged, and nothing. So if I do it, it doesn't matter, the total thing will be the same, right? So if I use dq reversible is equal to TdS, and I use dW reversible is equal to minus PdV plus work additional, right?
That's the total amount of work done. So
We are considering the expansion work plus whatever additional work comes out,
which could be because of the surface, which could be because of electrical charges.
and I substitute this back. So what I get is then TDS minus PdV dg is equal to plus W additional plus PdV plus VdP minus TDS minus SDT, and then this fellow, this go away, this and this go away, and since we are seeing the processes at constant pressure and temperature when we want to see the Gibbs tree energy change. So at constant pressure, temperature,
Right. And because this is a reversible process and dg is a state function, right? It does not matter whether reversible or irreversible, but dg would be equal to the maximum amount of work done additionally, because reversible work done is the maximum.
so I can always put a max over there. Yes.
dg would be, dg is a state function. It just depends on the initial and final points.
This is
Constant pressure temperature, right? Yes.
so it is an exception to that PV.
It is other than the PV work. PV work is this one plus additional work. These are the two kinds of work that could be possible.
Right?
Right? So when I do it reversibly, the maximum amount of work is done, right? I wouldn't have been able to derive this. Because I can't put TDS when it's irreversible or minus PDG. But then the total is the same. du is the same, right? So since it's a state function, and that would be equal to the reversible work done. So that is the maximum amount of work done. Yeah? Whatever way I do the work, otherwise, it will be always less than the reversible work. Yeah? That's all.
Okay. So then we are ready with a few things over here now. The criteria for spontaneity. Let me just sum up everything now. What have we seen? ds at constant uv or ds at constant hp greater than equal to 0, right? Then we had seen du at constant entropy and volume is less than equal to 0, dH at constant entropy pressure less than equal to 0. What else did we have? dA at constant temperature volume less than equal to 0, dG at constant temperature pressure less than equal to 0. These were the criteria for spontaneity that we have seen till now. And what else had we seen? We had seen some equations, some fundamental equations. One of them was du is equal to TDS minus PdV Then we had dH is equal to TdS plus PdV, VdP, sorry, plus VdP. Then what else do we have? We could have similar equations for A and G, right? We could actually work it out, because A is equal to U minus Ts, right? So let me just quickly work it out over here in the next page and then come back. So A is equal to U minus Ts, or dA is equal to du minus TdS minus SDT, and du I would pick up from here, TdS minus PdV, which is equal to TdS minus PdV minus SDT minus TdS, which is equal to minus SDT minus PdV, right? So I'll put that back over there, minus SDT minus PdV, and then similarly for G, dG is equal to dH minus H minus Ts, right? TdS minus SDT, and dH was TdS plus VdP minus TdS minus SDT, so minus SDT plus VdP, and I plug it back over here. dG is equal to minus SDT plus VdP. Okay. So what we have completely are these four equations, known as the fundamental equations in thermodynamics. From these fundamental equations, you can get a lot of information, lots and lots of information over here. For example, if I want to see what is the change in internal energy as a function of volume when the entropy is held constant. Might sound a bit abstract, but if I come down to dG, I would like to see, okay, what's the change in the free energy as a function of temperature when the pressure is held constant. It is minus S. What is minus S? The entropy of the substance, negative of that. Now, entropy of gas is maximum, right? So let me just plot it here. For example, G as a function of temperature. Entropy of the gas is maximum, right? So if I am in the gaseous state, then my entropy would be the slope of G with T. So the slope would be maximum with a negative sign. So the slope of a gaseous, the gaseous substance which I am taking would be maximum. Okay. If I now take the entropy of a liquid, it is less than that of a gas. So the slope would be less slanted, right? The slope would be something like that. If I take a solid, it would be even less entropic, less disordered. So the slope would be something like that. What do I get out of it?
That phase is stable whose entropy is maximum. So when I am at higher temperatures, I have maximum entropy of this gas. Right? When I come down to lower temperatures, the maximum entropy that I have is of the liquid. When I come down to even lower temperatures, the maximum entropy that I have is of the solid. And that's why at higher temperatures you have gases which are stable, then liquids in the intermediate, and low temperatures you have solids that are stable. This is a very hand-waving argument, but you can look at absolute numbers also and see that these kind of curves do exist for each and every kind of matter that we have. Okay, just one example that was, but other than that, let's look at a few more things over here. So we had the fundamental equations. And what else do we get from the fundamental? So these fundamental equations all have variables that are state variables, functions that are state functions. I can always apply the Euler's criterion to these state functions, right?
So for example, let's look at du is equal to TdS minus PdV. Let's look at this one. And let's apply the Euler's criterion over here. What do I get? Del T by del V at constant S is equal to minus del P by del S at constant V. Let's look at the next one. dH is equal to TdS plus VdP. What do we get out of here? Del T by del P at constant S is equal to del V by del S at constant P. dA is equal to minus S dt minus P dV, and this gives me del S by del V at constant T is equal to del P by del T at constant V, and the last one here, dG is equal to minus S dt plus V dP, gives me del S by del P at constant temperature is equal to change in volume with change in temperature at constant pressure. Negative sign, with a negative sign, thanks. Anywhere we can put it. Now, these are known as the Maxwell relations.
These are very useful in solving a lot of problems in thermodynamics, lots and lots. Because now you see, remember I always said it's very difficult to calculate some entropy or something. Yes. But if I know how it changes, how temperature changes with pressure at constant volume, or how volume changes with temperature at constant pressure, I can get an idea of the entropy. What is the change in entropy? Yes. So these are things which can be related.
You could even derive the identities which I've told you already and you've been waiting for. Pi t, for example. Right. So again, going back over here, pi t was del u by del v at constant temperature. So I could use the first identity and try to get whatever I achieve. Del u by del v at constant temperature would be equal to TdS, right? T del S by del V at constant temperature minus P dV. Minus P dV by dV is 1. Yes? And then look up the Maxwell equation for del S by del V at constant temperature. The third one is equal to del P del T at constant volume. So what I get is
This is the identity that I have given you. Right?
I could get the other one also. So again, I go back and look at the second one. T del S del P and del S by del P at constant temperature is equal to minus del V by del T at constant pressure, the fourth Maxwell's relation. So from there I can easily get minus, there's a minus sign over there. Right? These are the two relations which you've been already using for quite some time. I don't find these relations very difficult to remember, at least the fundamental equations. Remember those? Then, or if you just remember du is equal to dq plus dw and change it to reverse equal to tds minus pdv, derive the rest of them. Or some people use something called a thermodynamics square. It's kind of a mnemonic to remember. But I really don't feel very comfortable with, anyway, I'll just tell you. But it should not be that you make more mistakes by looking at this square. So start from the bottom of the square and write all of these functions in alphabetical manner counterclockwise. So A, G, H, U. Okay. And next to each one, write the common variables. So between A and G, temperature is the common. Normally, we use volume and temperature as the variables for A. We could use anything, right? We could choose anything, but what we choose is the natural variables we choose are temperature and volume. For Gibbs free energy and enthalpy, we choose pressure. For H and U, entropy. Okay. and then you make some arrows over there like that. So now, for example, if you want to look at how to write du, so du is equal to the variable on the far of it times the differential of this on the diagonal, right? So du is equal to, for example, if I want to calculate u, then I take the furthest variable, this variable on the far, 1, right? And of course I'll have to take the other variable which is on the far, yes, but since this t has an arrow towards it, it will get a plus sign, and since p does not have an arrow towards it, it gets a minus sign. So du is equal to t ds minus p dv. I don't know. If you find this useful, use it. If not, leave it. Okay. I particularly am not too fond of this. Or it's given in some books and you want to give it. Okay. So what else do we have for now?
Now, the thing is that we've already seen the way we calculated dg or dA or dH, everything came from u to start with. Came from the first and the second laws. Now the thing is that we could actually put all this formulation in terms of one variable. And the variable so useful is the Gibbs free energy, because most of our work, most of the reactions that we do are at constant pressure and temperature. The lab conditions or the daily conditions which we normally face are constant pressure and temperature. So there are some special circumstances where you would prefer the Helmholtz free energy to the Gibbs free energy, but more often than not it's so everything you can formulate in terms of the Gibbs free energy. You could even formulate in terms of the Helmholtz free energy, but I'll just take up one of these, the Gibbs free energy, for example.
So let's write the fundamental equation again. dg is equal to minus s dt plus v dt, right? And from here what I get is that let's try to put all the variables now. S is equal to minus of dg by dt at constant pressure. We've seen this just a few minutes back. I showed you what exactly it means, right? We could actually say which one is more stable, the gas, liquid or solid, by just comparing the entropies. Then volume would be given by dg by dp at constant temperature. H, which is the enthalpy, is G is equal to H minus Ts. That's the definition. So H is equal to G plus Ts, right? So if I know G, I know, well, of course I know the temperature, pressure, volumes, right? At least something I must have, some information. The entropy is minus of dg by del G by del T at constant pressure. Right? I could write the Gibbs free energy, the internal energy. If I already know the enthalpy, then I can write the internal energy, right? H is equal to U plus PV, or U is equal to H minus PV, which is H is just given above, del del G del T at constant pressure minus P volume is del G del P at constant temperature. So entropy, enthalpy, internal energy, Helmholtz free energy. That's U minus Ts, right? So H was G plus Ts, this is U minus Ts. So this is H. That means the second term goes off. What I am left with is G minus P del G del P, right? Then I had defined Cp was equal to what was Cp equal to? Del S by del T at constant pressure. That was Cp by T. Yes? So this is T times del S by del T at constant pressure, which is equal to S is equal to minus del G by del T at constant pressure. Huh? Ah. Del S by del T at constant pressure. Also, if you remember in the last lecture we saw Cp by T was equal to del S by del T at constant pressure. Yes? Get it from the fundamental equation for dH, nothing else. So this is nothing but minus of T del square G by del T square. So essentially you can get all the information that you want starting with any one. If you have information about one variable G, or for that matter A or U or H, you can get information about the rest of the thermodynamic functions. They are all related. Yeah. Any questions? Okay, we had seen just now. We had seen that S is equal to minus of del G by del T at constant pressure. So if I plotted G as a function of T, then S was the slope. Volume, that's the change of Gibbs free energy with pressure, right? So if I plot the Gibbs free energy as a function of pressure, now the thing is that would be equal to volume. The slope would be equal to volume. Think about solids or liquids. If I actually change the pressure, if I apply pressure, volume does not change much, right? It remains constant. So which means that the Gibbs free energy at a given pressure and at a separate pressure at two different pressures is more or less the same for a solid or a liquid. But if I go to gases, then of course there is a lot of change. So in general, for solids or liquids, I would say that the Gibbs free energy, is simply a function of temperature, roughly, approximately, let's say. But in the case of gases, what I want is change of Gibbs free energy as a function of pressure. Temperature is held constant, it's given by volume, right? And if I am doing it for 1 mole, then it would be molar volume, nothing else. But what I would get is the change in the Gibbs free energy at, let's say, pressure 2, temperature T, minus or is equal to, if I integrate this expression, is equal to G at pressure 1, temperature, plus V dP from pressure 1 to pressure 2. Yes, this is the part that I have ignored in the case of solids, and that's why whatever Gibbs free energy is at pressure 2 is equal to Gibbs free energy at pressure 1, so it's only a function of temperature. Now the entropies do change for solids, liquids, gases, right?
So why we have just neglected it for solids? Because changing dP is in our hands.
Yeah, so if I, okay, now if dP is large, think of processes where huge pressures are involved, graphite being turned into band. So pressures in the crust of the earth, for example, those are huge pressures, then I cannot ignore. Okay, I am talking of small changes in pressures. Right?
If the pressure changes, we can neglect it for gases too.
No. Volume of gases changes a lot. Volume of solids, and I change the pressure, it does not matter much. Yes, so let me just mention that over there. For small pressure changes for liquids, solids, right? Yeah, if the pressure change is large, of course there will be a change. Then we'll have to include this term. But in the case of gases, we could just take an ideal gas, for example, and what we would get is G at pressure 2, temperature T is equal to G at pressure 1, temperature T, plus RT log P2 by P1. Yes? And if I decide to take P1 is equal to some standard pressure, which I would normally take as 1 bar. So let's take P1 is equal to some standard pressure, which is equal to 1 bar, and all my pressures are reported in bars. Okay. So then G at P2 is equal to G at P1 plus RT log. So this is also RT log of P2. Instead of writing G at P1 temperature, what I write is G, the standard one, at temperature T. And then I don't even have to worry about P2 or P1 because this is for whatever pressure. That's the way I define the Gibbs free, the change of Gibbs free energy with pressure. So I should know the standard Gibbs free energy, that is at 1 bar and the given temperature. Then I can calculate the Gibbs free energy. So this is for an ideal gas, right? At a given pressure and the temperature. Just R log T. Likewise, I could have, since entropy is nothing but equal to the negative of the slope of Gibbs free energy with temperature plot, S is equal to minus del G by del T at constant pressure. If I do that over here, then this is S at whatever pressure at temperature would be equal to S some standard entropy, that is the entropy at 1 bar plus R log P. Sorry, it's a minus sign. Minus of dg by dt, minus of dg by dt, so plus, so there's a minus sign here. There's a minus sign here. And okay, so since we are not using the number of moles, let me then formally write this as G bar or G molar. Let me write the molar. It's the same thing. G molar, S molar, S molar, right? And this has a name, and that's why I just wrote it. This is called the molar Gibbs free energy. The Gibbs free energy per mole is also known as the chemical potential. It's denoted by mu. And in the next class, we will go on to mixed systems, where we will see what is the need to use this chemical potential. So everything tends to flow towards the direction of a lower chemical potential. Yes. I mean, always I just use one mole. So why not? Let's write molar. That would be more proper to write, right? That's G molar, nothing else. For the moment, it's G molar. Go on to multi-component systems, I'll tell you what. Questions? No, activity will come when it's a solution. We'll come to that. This is just a question. Remember this. this P always in bar,
always. Now, since you brought up that question, a quantity that is an argument of a log cannot have any units, right? So this is actually P by P1 or P by P naught or P by 1 bar. This is, all of these are unitless. We come to equilibrium constants, and all the equilibrium constants, they don't have any units. This is one thing you should always remember. Rate constants do have, but equilibrium constants don't have any units. It's from here that we'll derive all the equilibrium constants also. We'll do that later. Okay. If you don't have any more questions for today, then I'll stop here, because then we go on to the multi-component systems, and that I will try to start next time. So we could have some question answer session, or if you want to clear some doubts. Let me stop this.